And I'll show you why. So, we were in the process of discussing open and closed systems. So chemical reactions can occur in both open and closed systems. An open system is defined to be a system in which energy and matter are able to enter and leave. Energy and matter are both able to enter and leave the system. This classroom right now is an open system. If you wanted to, the door's open. If you wanted to get up and leave, you could. The door is open. It's not locked. There's nothing stopping you. You are matter. You could leave. Energy can also leave. We'll talk. That's less interesting. Let's close the system. Now you cannot leave. You have the door, and you have me to deal with. Closed system. But if we wanted to, energy could still leave. Energy could leave this room in what form? Who said air? Air is not energy. I'm not going to. Don't tell me who said it. Air is not energy. Matter is not allowed to leave the room. Air can't get in or out. Well, it can because there's a little crack in the door. For some, this is an open system. For others, it is not. Energy can't, though. Why not? Energy can leave. How does energy leave? Yes. Sorry? Electricity is technically not energy, but electricity can be used to produce energy. What kind of energy? Sorry? What's energy? We're talking about energy. How does energy leave? Who said? Sorry? Sarah? Louder? Light. Light is not matter. Light can come and go. There's open windows. Light's coming in. See, if I turn these off. This is still a closed system. The light is still coming in. It's not totally dark in here. If I wanted to, we could shine another, this is a higher energy light onto the trees out there. I wanted to shine it into Mr. McGree's classroom over there. I totally could. Energy can leave in the form of light. Energy can leave in what other forms? How else can energy leave? Sorry? Heat, you betcha. We could start a fire in here. It would radiate out. If I put the fire next to the door, the fire's not leaving. The thing that's burning is not leaving. But if there was a fire here and you were over there, you put your hand on the door, you feel it. It's interesting because heat is light, believe it or not. It's just this part of light. This is a poster. This whole poster is everything light. Everything on this poster is light. Visible light is just this rainbow colored section. Right below it, this is heat. Right above it, this is UV. Down here, this is a radio. So radio waves are bathing. Radio waves, like if you could turn on a radio right now and get a signal, whatever your favorite station is, this is still a closed system, but you can pick up a radio signal. How else can energy show up in not light? Tell me. Sound. If I wanted to get Mr. Keeley's attention right now, could we? Without leaving the room, without anything physically passing from here to there, if we all in unison yelled for Mr. Keeley, would he hear you? Yeah, probably. Why? Because sound could we test it out? Yeah, come on. Okay, so then in unison, can we all practice quietly? Okay, we're going to say, hey, Mr. Keeley. Okay, let's do it quietly, and then we'll yell it in a second. Okay, 1, 2, 3. Hey, Mr. Keeley. That was really bad. Let's do it again. 1, 2, 3. Hey, Mr. Keeley. Okay, cool. Now we're going to do it really loud. On 3. 1, 2, 3. Hey, Mr. Keeley! Oh, let's see if he hears us. Let's see if he comes. So nothing left from here to there. So So how is that energy?
He's coming.
Is he coming?
Yeah.
See? You're not writing. I checked. You're not writing a test. We were modeling the closed system. We're talking about how energy can enter and leave. Nothing went from my classroom to your classroom, except for me to make sure that you weren't busy in the middle of the lesson. And then we demonstrated that you could still hear us. So energy left this classroom, went into that classroom.
It wasn't necessarily the energy that left the room, it was the fact that my hearing is still pretty good at my age.
Well done. I wasn't sure if you were going to respond. So, closed system. Closed it wasn't until he came in the room. How did he hear you? If nothing moved, what is sound? Thank you.
I'm glad I could feel the system.
I had two. Sorry? But what is sound? Sorry, Emma? It can be transferred a bunch of different ways. Well, likely not. The easiest way for it to transfer it, so it's just a vibration. It's a vibration of a medium. So in this case, we've got air. The air didn't go anywhere. The air didn't go from here to there, carrying this message. When we all yelled together in unison, it's just kind of a sound wave moves back and forth. Some waves go up and down. Sound wave moves back and forth. Take my physics 11 class. We do a whole unit on waves. But sound is a wave that just moves back and forth. And so the air molecules just move forward. They bump into the next thing, and then these ones bounce back, and these ones bounce forward, and these ones bounce back, and it just keeps going. And then it hits a wall. And then the wall vibrates. And then the vibrations go through the wall. And on the other side of the wall, the air on the other side picks up that vibration and keeps going. Yeah? Yes. The louder you are, the stronger the vibration is going to be. And there are theoretically things that can be built into this wall to dampen that vibration. That's how you soundproof a room. But even then, we've still got this. So glass is going to be a really good transmission of vibration. And sound actually bends around corners. Take my physics 11 class, we'll talk about how sound bends and why that is. So we've got an open system and a closed system. Nobody left in the closed system. The matter remained. And yet energy was able to come and go. So this one, energy in the closed system, that's this first blank here again, but energy in the form of what? Heat, light, and sound. Heat is light that you feel. Light, when I say light, when we talk about visible light that you can actually see. And when you think about heat being the light that you can feel, it sounds weird to say that, but that's what it is. It's the same thing with when you get a sunburn. UVA, you guys cannot see UV light, but you know UV is a light. We think about it as being a light all the time. We know that it's produced by the sun. UV light will burn you. You can feel that process happening if you don't fall asleep in the sun. But heat, like the boiling of the water on the stove, that's light being emitted that you can feel. It's weird. And then sound, obviously, you sense that a different way. It's a different way energy can get transferred. Energy can enter or leave. Matter cannot. Matter stays the same. And so I've got two here. This is a flask. We're going to use a flask today. An open flask, matter can enter and leave. And this is clear glass, enter and leave. You can hear, even if it wasn't clear, heat could still get out, sound could still get out, but it's clear, so visible light can also get out. You put a stopper in it, which you're going to do today. Make sure that stopper doesn't have any holes in it. And you've now created a closed system. This system is closed, this one is open. A simple concept, but kind of a profound, yes, Evelyn, result. To trap it? Just forever? No. Because, I mean, you can trap it in the sense that it will get, like, you can perfectly soundproof a room so that no sound can leave and no sound can enter. There is one room on the planet that is perfectly soundproof to the point that you can stand in it and you can hear your own heartbeat. Like, it's
All of the extra noise has been cut out. The only noise that's made is whatever is produced by you. And it's, from what I understand, it's actually a very eerie experience. Like, people can't stay in there for very long because all of a sudden now you're being exposed to sounds you've never heard before. So in that sense, you can trap and isolate sound. But if you're talking about just like, if I just yelled once and that sound gets bounced back and forth forever, that's not going to happen, because sound, as we discussed, sound is the sounds that I'm making. I'm vibrating air in my vocal cords that's hitting other air, that's hitting other air, that's hitting other air, that hits you. It's not like a wave that goes directly from me to you. It's jiggling air molecules back and forth, and when air molecules hit each other, they heat up. And so you're losing sound energy in the form of heat as that sound wave moves back and forth. And so that energy is always going to get transferred into heat, and you're going to lose that heat. It's why the echo is not as loud as you were, because the echo goes out, the echo comes back, but the energy involved in that wave is dissipating into other forms as well. Generally heat. You are heating, and then it also depends on how much moisture is in the air. If the air is really, really dry and really, really cold, sound waves will travel further. As soon as you put in moisture into the air, that makes it harder for the air molecules to jiggle. It dampens the sound. As soon as you increase the temperature, the air molecules are actually less packed together. It's harder for that wave to transmit. Take my physics 11 class. We do a whole unit on waves. It's really cool. So in this closed system, open and closed system, in the late 1700s, this became a big deal. It's not a very difficult concept, but it has some very profound implications. A French chemist named Antoine Lavoisier, very important name in the history of chemistry, greatly advanced the understanding of chemical reactions. Before him, no one had decided to sit down and take the time to do what he did. He performed a bunch of experiments. One experiment he repeated a whole bunch of times, and that's the one that we're going to talk about. He performed many experiments in a closed system that he had designed, in which he measured the mass of the chemicals before. And in the reaction we're going to talk about, it was one chemical. He took one chemical, he put it in a closed system, and he heated it up. That's all he did. He was able to measure the mass of the chemical beforehand. He performed the reaction and then measured the mass, or the masses, of the substances. There were two substances created after the reaction. So he started with one. He heated it up, is all he did. And he caused what we will later learn is called a decomposition reaction. And he was able to separate and isolate the two different compounds and weighed them and found something kind of interesting. Flip the page. This is the apparatus he used. The reaction he did, and I'm not going to get into all the nitty-gritty details of it, but as a general kind of overview of the reaction, what he did was he took mercury 2 oxide. So mercury 2 oxide, mercury is Hg. Roman numeral 2 means it has a charge of +2. And oxide, which is O minus 2. So mercury 2 oxide has what formula? HgO. He took mercury oxide, which is a solid, a red solid, and he heated it up. This compound breaks down when it's heated. It's called a decomposition reaction, which we're going to look at in more detail in a couple weeks. And when it breaks down, or when it decomposes, it forms a silver-colored liquid. That silver-colored liquid is pure mercury. At room temperature, mercury is a liquid. So if you heat it up, or if you heat mercury oxide up, you will effectively melt the mercury portion. It'll become silver. The red will turn silver. And you will also produce colorless oxygen gas. So he had his apparatus here. So this kind of weird teardrop shaped thing would have been made of glass. He likely, so in this setup here, so he put the mercury in here, the mercury 2 oxide in here, ran this under some water to cool the gas that was being created, to condense it. And this bell over here, he likely tried to pump as much of the atmosphere out of that thing as he could, so that there was nothing left in here. This contraption allowed him to trap the mercury over here and the oxygen gas over here. The mercury went over here, and the oxygen went over here. Because he was able to collect them separately, he was then able to measure their individual masses. And interestingly, he did this reaction a couple hundred times. He found that the mass of the HGO, the mercury 2 oxide at the beginning, was the same as the total mass of all the pure mercury and the oxygen gas produced every time. So the mass of the HGO was the same as the pure mercury plus the oxygen gas. This is a very profound result, because he was then able to throw down what we call the law of conservation of energy, which is what goes in here. The law of conservation, sorry, it's not of conservation of energy, that's physics 11. This is the law of conservation of mass. There are a handful of conservation laws in science. Each one of them is profoundly important. The conservation of energy says energy can't be created or destroyed, it just gets transferred. We'll look at that in the physics unit. The law of conservation of mass says mass, or matter, cannot be created or destroyed in a chemical reaction, just moved around. Which is fairly profound. And there's all sorts of it's kind of common sensey, but on the other hand too, makes a lot of sense. If you're in a closed system, like if we were, for whatever, we were to isolate this room, we had the food in here that we needed. We had a way to store whatever waste was produced. As time went on, you guys would be eating and drinking. We would all be eating and drinking. We would be expelling waste. The food would go down, but the waste would build up. Like, it's the idea that matter just kind of moves around in cycles, I think, makes inherent sense. But for him to actually stop and put it together to create this law of conservation of mass, matter cannot be created or destroyed in a chemical reaction, just moved around, was really quite profound. It means that if you're losing mass, for example, like you're in the lab that you're going to do for me today, you're going to perform a reaction in an open system and in a closed system. In an open system, matter is allowed to come and go. And so we're going to prove that by allowing something to go. If you can see that mass is leaving, that means that there must be some, even if you can't see what it is that is leaving, which you're not going to be able to today. If the mass of your reaction drops, that means there is something real, something physical, something tangible that's leaving your workspace and going somewhere else. And for chemists back in the 1700s, early 1800s, it was a really good indicator that something is going on here that we don't know, which is really quite profound. It meant that if you wanted to start isolating different elements, if you wanted to pull, I don't know, even in mining, if you wanted to pull out, if you wanted to purify gold out of something, for example, you can't get pure gold necessarily. Generally speaking, you pull something out of the ground and you process it. It means that in that process, if you can pull out, well, it means that you are able to pull out whatever it is that you're looking for that's mixed into other things, or that you can combine things to produce a certain amount of stuff, if that makes any sense. So it was really quite groundbreaking in the world of chemistry, and that's what we're going to go to the lab today to look at. So you can leave your stuff, grab a writing utensil, and I'm going to talk through the lab before we go. You guys are going to work in 2s or 3s. I don't want anybody doing this alone, just because we don't have space or the right amount of stuff. So just have a seat, grab a pencil, we're going to talk through the lab, and then we're going to go. I don't want to talk through the lab. In the lab, I want to get to the lab and get you in there. This is a 2-part lab.
So this scientist and whatever that is. Even though he like split the oxygen and
Okay. That's that. Okay, so we'll talk this through. This is the procedure. Your observations are going to be the second sheet that I gave you, but I don't need to give that to you quite yet. So this is a 2-part lab. One of them is going to be an open system, one of them is going to be a closed system. The first one you guys are going to look at is a closed system. And in a closed system, matter's not allowed to leave, energy can come and go. So in a closed system, the reaction that you're going to do, the mass should do what? Should stay the same, which is kind of a boring result. You're going to mix some things together like, oh look, it weighed this. And you're going to mix, and like, oh look, now it weighs the same, is what you should verify. If it doesn't, that's really interesting. It's happened, but that's what you should see. So that's part 1. You're going to need a 25 ml graduated cylinder. Before, you're going to use some dilute sodium hydroxide. Sodium hydroxide is a chemical component of similar to bleach. You don't want to get this stuff on your clothes, but it's weak. It's not a very strong one, so if you get it on your hands, you can wash it off. If you don't want to get it on your clothes, then bleach your clothes. You're going to need a 25 ml Erlenmeyer flask. This is the flask. It's the one that starts with, and it has a neck, and then it has kind of a large bottom. Okay? You'll need a 250 ml Erlenmeyer flask. Not 500, 250. You're going to need some dilute iron 3 nitrate solution. They're the yellow bottles at the front of the glass. A small test tube. It says small test tube. Your test tube needs to be able to fit inside the flask. That's how you're going to know whether or not your test tube is small enough. So you'll need the flask and the test tube. If one can fit inside the other, you're good. You'll need a rubber stopper. There are many rubber stoppers. You just need to find one that will fit the flask that you've chosen. I have pulled out the box that will most likely work, but if it doesn't, I will direct you to the other boxes. You can find a stopper that works for you, for your flask. And you're going to need an electronic balance. So we have the silver ones that you guys used in the first lab that we did, the lab equipment lab. I've only got 5 of those. I don't know where the other 3 went. So some of you are going to need to go to the side of the class and grab the bigger electronic balances. They're in the cupboard with the lab. I'll show you where those are. That's part 1. The procedure is there. I'll talk through it. You're going to grab both solutions. The NaOH is going to go into the flask. The yellow iron nitrate solution is going to go into the test tube. You're going to put the test tube inside the flask, not tip it over. You're going to put the stopper on it, and you're going to weigh that whole setup. You're going to make some observations, which you're going to record on your observation sheet. And then you're going to mix it. When you mix a flask with a stopper, there is a way, I didn't explain this in the first class, and then when you have something inside a flask and you want to mix the thing, grab it by the neck, put your thumb on the stopper, and then do this. Don't grab it by the bottom and do this, because then the stopper can come out and then make a big mess. So then you're gonna make a bunch of observations. Something interesting will happen. Make some observations. Weigh the thing, and then part one is done. There is a waste beaker for the products of the first reaction. Then part two. Part two, you have a table that you're going to fill out. You are going to use water in a 250 ml beaker. That's beaker. Flask, test tube, beaker. You're going to put 100 ml of water in a 250 ml beaker. You're going to put that on a scale. And you have an Alka-Seltzer tablet. Also goes on the scale. You weigh them all together. You make some observations. Take the tablet. After you weigh it, you take the tablet, you drop it in the beaker, leave the beaker on the scale. Has anyone ever played with Alka-Seltzer tablets before? Yeah? What did you do? Yeah. So like when I was in elementary school, we made, one of the things you can do with them is you can make little rockets. Film, wait, you guys don't know what film is. Maybe not. Does anyone know what film is when I say film? Yes, what are you thinking of? And the camera, yeah. So back in the day, like regular camera, like old school cameras had film. They came in little, the film came in canisters about yay big. You take the film out, and then you put it into the camera, and you pull it, and you close the camera, and then you actually had to, it wasn't digital. Those canisters, we actually in elementary school made Alka-Seltzer rockets out of. Because when you take Alka-Seltzer, put it in water, as Evelyn said, it fizzes. You're going to produce something. In a closed system, that fizz is going to build up, increase the pressure, and in a rocket, it will boom. Which is why we're doing it in an open system. This is going to prove our open system. You're going to weigh together, this goes in there, and you're going to continue to weigh the thing the whole time. Every 30 seconds, you're going to record the mass of this thing as it reacts until the mass stops dropping. The problem with this is that if you grab one of the little gray scales, it's the better scale to use, but because it's battery powered, not plug-in, it will turn itself off after a predetermined length of time. I don't know how long that is. So, to make sure that it doesn't turn itself off, you need to push on it, like onto the weighing part every so often, because large changes in the mass on the scale, and the reading of the scale, will keep the scale alive. Small changes in mass, like what you're recording, aren't big enough to keep the electronic device moving. Okay? So every so often, just push on the thing, every 30 seconds, as you're recording the data, every 15 seconds, push on the thing. As soon as you let go, it's going to go back to whatever the mass of the water, Alka-Seltzer, and beaker are, so that you don't lose all of your data. You're going to continue until most of the bubbling has stopped. Some of the Alka-Seltzer tablets are really, really quick. You can be done pretty quick. Some of them take quite a while to do. You have lots of time to do it. So that's what you're going to do to both sections of the lab. First thing you're going to do when you get into the lab is to grab what? Goggles. Thank you. If you have glasses, that's fine. If you need it, there's no fire on this one, so you don't really need a hair tie. You just need to put your hair behind your head. And if you have glasses, that's fine. If you don't have glasses, grab some safety goggles and start collecting the equipment. Once you have all of your equipment for the parts that you're going to do, you can come start to get the chemicals for me. They need to stay up at the front. I don't have enough to disperse them all onto all the different tables. You're working in pairs or in threes. Please, nobody working alone. If you've got questions while you're working, let me know. On your way out, grab one of
Thank you, Mrs. Lim.
Thank you, you got, thank you, girls.
Yeah, really kind of you. Okay, so let's get this together here. Each is supposed to hit ourselves. Okay, so we're gonna wait till Mr. D gets here. Here. And then pick it up. We're not going yet, we're gonna wait for the whole class to get out here. There we go. There we go. Exactly, man.
Sarah, Pastor Jim, what time did you?
I just had.
I like having them see walk.
Yeah, so you have to get up.
I like having them see.
Oh, okay.
Hey, grads, if you ordered grad photos, guess what? They're here. Come on down to the office. Be patient. You can pick them up. Grade 12, so many photos in the office. Come and get them. We don't want them sitting here forever. Come on and get your grad photos. You paid the money for these.
Okay.
Student was looking for you, but
Which one?
I don't know. Probably one from your physics one.
Should have told them to stick around. If you want to find someone, the best thing to do is not go anywhere.
Well, she asked me, do you know where Tweetup is? I'm like, nope.
In the lab. Now I'm back.
And I thought in my head, well, you got to prep after lunch, so maybe you. Might
Oh,
all-
my room's open.
I'm not coming.
you know, you're supposed to.
Nice. Hey, what's up? Where you been?
Yesterday I went to the doctor for my ankle. I sprained it really badly the night before and I thought it would get better, but it didn't. And then I went there and they just gave this like massage to the leg. And I was just laying
There's a
there.
sprain. There's nothing they can do.
No, there was like it was just
You
like
just gotta walk.
yeah. I've been stretching it out as much as I can, but today I heard it again in gym class. Yeah. Did you still wanna? I sent you a message. You can
Yes, I did, and I
That
forgot
was
to
so
reply.
mean. You should have replied.
Life happens.
He's got a life out
I
there.
appreciate your concerns regarding
Yeah.
where you're at. My only thought is a whole ton of this is technically a review of stuff you did in Math 10.
Yeah.
And you got 75% in Math 10, according to your transcript.
Yeah.
And so I want you to try it. Friday morning.
Do you guys have completion days here?
What's a completion day?
There's no completion days?
What's a completion day? We might have it. We just call it something different.
Basically where there's 2 days between the semester where you go to a teacher's class and you
Between semesters?
Yeah.
Oh yeah, so that would have happened already.
Yeah, and then it's like at the end of the year,
Yeah.
there's 2 days where you can come
Yeah.
in and
Yeah.
do your work.
Yeah.
Okay, what if it's like,
No.
What do you mean no?
Because you need those skills for stuff we're doing now.
But like,
I don't care about how you do it at the end of the semester.
What if I do like really well in what we're doing right now? Because I feel like I understand it.
I want you to write the test. Because you need those skills. We're going to be doing a bunch of graphing. You need the unit conversion stuff. You need the algebra. I want you to write the test this week, Friday morning. Is it tutorial or is it SLO this week? Tutorial Friday morning. Because then, at the end of the semester, on the final exam, if you show me by the end of the semester that you've learned the stuff that you feel you might struggle with on this test that I want you to write on Friday, I will omit the test. I don't want you to write at the end of the semester. I want you to write it now because I want to see what your skills are at now. And if you improve, I should probably not be recording this whole conversation.